Welcome to lecture number 2 on transformers. In the last session, we studied uh, what is a transformer, why we use transformers, and based upon that, we studied different types of transformers. In this session, we'll start with the construction of transformers. So actually, depending upon the power rating of a transformer, you may have different constructions, uh, requirements, requirements of a transformer, and accordingly, the transformer uh, will vary in shape and size. Uh, Naturally, for a higher power rating, you will see that the size of a transformer will be very high. It will be huge, and for a small power rating transformer, as you see in normal residential applications, the transformer is very small. And if you go even at electronic level, even there you may see mobile chargers have transformers. That these are actually high frequency transformers, and the size of these transformers are uh, as small as fingertip. So, depending upon your power rating, your transformer size will change. Depending upon the frequency, your size of the transformer will change. And uh, so, uh, normally, when we talk about transformers in power systems, we classify on the basis of construction, we classify them into two types. One, we have a core type transformer, and secondly, we have a shell type transformer. Uh, so both core type and shell type, the principle of operation will be similar, but as you see, in case of a core type transformer, the uh, structure of the core will be rectangular. Core basically refers to that part, that component of the transformer, which actually supports the windings. If you see, the windings are actually wound around the core of a transformer, and these windings are actually placed in a specific manner. We'll come to that also. So in a core type transformer, you have a simple rectangular structure, while as in case of a shell type transformer, you have a double core structure. You have actually shell type structure wherein the arrangement of windings will be done in a specific manner. Now, what happens in case of a core type transformer is that the low voltage winding, I will not be now referring to as the primary winding and the secondary winding. I will be referring to these windings as the low voltage winding and the high voltage winding. So normally the winding is actually wound, if we take a simple core. So you see actually the windings are done uh, in such a manner that the windings are actually wound around this transformer, around the core of the transformer. So these cores are actually made up of you actually have these cores are actually made up of steel, whether it's a core type transformer or a shell type transformer. These are made up of laminated steel rather. We come to the term laminated as well in shortly. So these cores we are made up of laminated steel, and the windings they are actually done around the core of the transformer. The windings are actually wound around the core. Fine. So normally when we in this is not the actual configuration, but when we actually refer to the transformer, the convention is to show the transformer like this. We say this is the primary winding, so this will be the winding where you will be exciting, and this is the secondary winding. Fine. So this is not the actual structure. We do not wind the windings are not done in case of a transformer, the windings are not done in this manner. You do not have primary winding on one side and the secondary winding on the second other side. You have both the primary winding and the secondary winding on both the limbs of the core. Fine. So these are actually known as the limbs of this core. So this is the main structure, laminate, made up of laminated steel that actually supports the windings. The convention is to show the transformer like this, but this does not actually, this is a pictorial representation that you'll see, you will come across in various books, but this is not the actual representation of a transformer. Windings, in case of a core type transformer, they are done in this manner. First of all, I would also like to know, highlight the dimensions of this transformer. What you can see in case of a core type transformer, all of the flux will be linked in this, will be actually concentrated in the legs, in the limbs of the transformer. What happens in case of a shell type transformer, this limb, this actually the central limb, the width of this is, if the width of this is B, the side limbs will be of dimension B by 2. Fine. So width of the side limbs is B by 2 if the width of the central limb is B. What happens in this case is that if flux phi is concentrated through the central limb, phi by 2 will be flowing in this path and phi by 2 will be concentrated along this path. This is around this about the dimension of the core type transformer and the shell type transformer, and how the flux is actually distributed in this. Now, what you will see in case of the core type transformer is that the LV winding, will be wound first. So this will be LV, this will be LV winding, and on top of LV winding, you will be winding the HV winding on both sides. Similarly, in this limb also, LV winding will be here, HV winding will be here. LV winding, HV winding. What you can see in case of a core type transformer, the LV winding is to the is actually concentrated towards the limbs of the transformer, while as HV winding are actually concentrated on top of the LV winding. Both on this limb as well as on this limb, you can see that the windings are actually we actually wind on both the windings are done in on both sides of the transformer. It's not actually windings are done. LV winding is you have one primary winding on one limb and secondary winding on the another limb. Both limbs, in case of a transformer, carry the LV winding as well as the HV winding. Now, why we actually prefer this combination, where LV winding is actually the low voltage winding and HV winding is the high voltage winding. I'm not here referring to the primary winding and the secondary winding. So why? Because a transformer can be step up transformer, it can be a step down transformer. So the primary winding can actually be having higher voltage or lower voltage. So if it's a step up transformer, the primary winding will be having lower voltage as compared to the secondary side. If it's a step down transformer, the primary side will be having higher voltage as compared to the secondary side. Now we prefer to wind the lower voltage windings internally onto the internal parts of the limbs, while as HV winding is done on the external part of the limb. So, using this winding the so actually winding in this manner the transformer, uh, the low voltage side, the low voltage winding being internal towards the limbs, you can actually note that the potential difference between LV and the core of the transformer will be less as compared to the potential difference between the HV and the core of the transformer. Right? So if the potential difference is less, circulating current will be less. Also with this winding the transformer in this manner, the insulation requirement will be less. So you can actually see that there are a number of reasons for doing this. Insulation requirements will be less. And secondly, uh, the insulation requirement will be less because insulation between LV winding and the core will be less as compared to if you had placed the HV winding with the limb of the core. Fine. So you would have required more insulation there. So in this manner, if we do the windings, the low voltage windings towards the limb, the insulation requirement will be less. Also, the potential difference being less, the circulating currents, the losses in the system will be less. And similarly, what we do in case of a shell type transformer, if it's a shell type transformer, I'll show a zoomed version here. If this is your one, this is your shell type transformer. The LV winding is placed like this. Then you will have the HV winding. Then you will again have the LV winding. Then you will have the HV winding, and then you will have the LV winding. The difference here being that the breadth of this LV winding, if it is say for example D, then the magnitude of depth of LV winding in the central, that's actually central to this, will be 2 times D. That means the windings will be more in this transformer. So this is actually what we do in case of the core type transformer and the shell type transformer. These are how the windings are placed. The manner of placing the windings in this particular fashion reduces our insulation requirement. We require lesser insulation in this fashion, as well as the potential difference being less, the circulating currents will be less, losses in the system will be less. So the transformer will be more efficiently designed. So this is about your uh, windings and how the core of the transformer is placed. Now we also had pointed out that the core is actually laminated. So this core is actually a solid structure like this. If we talk about, if we show this in a 3D manner, this is how your core looks like. Fine. So we have a solid structure around which the windings are done. Now this solid structure is basically made up of number of laminations. So laminations means we actually take thin sheets of steel, we place them. You may have one sheet of steel. This will be one sheet. We'll have then another sheet of steel. So you will place them on top of each other and make a stack that will actually form your core. Now these sheets of steels are not actually rectangular in nature. They are actually they can be of different shapes. They are not definitely they are not rectangular. So you do not have one solid block of steel that is used for the core. You will have sheets of steel that will be stacked upon each other that will form a solid core like structure. Now these sheets will be actually of different shapes. You can have a U-shaped structure. You will have an I-shaped structure. You will have for a shell type transformer, you can have an E-shaped structure. Fine. UIE. So these combinations of laminations, these combination of steels, which are actually referred to as laminations, are used. They are stacked upon each other so that the core is basically constructed. Fine. And one more thing, what we do in case of transformers is that this core is actually tapered. That means it's actually somewhat circular in nature, uh, not exactly circular, but at the center, the core of the transformer has more diameter as compared to its peripheries, and this is actually used for uniform flux distribution. Fine. So now why we actually use laminations, why we do not use a solid block of steel, why we go for these sheets and stack them upon each other. So once we actually stack them, we actually laminate them in between. They are actually using say for example laminations, varnish extra, you can actually separate these sheets of steel, so the reluctance of this magnetic path will actually be increased. That means the flux in this core will actually be one, the reluctance of this path will be more, so the flux distribution in the core will be less as well. uh, Reluctance will be less, so net flux will be more. And secondly, the eddy current in this sheet will be reduced. So these laminations are used. Laminations, the purpose of using laminations is to reduce the eddy currents. So if you reduce the eddy currents, you can actually reduce the eddy current losses in this system. So this is all about the construction of a transformer. You have a core type transformer, you have a shell type transformer. Core type transformer, it's a simple rectangular structure, while as a shell type transformer, shell type wherein you have actually side limbs and a central limb. The central limb having more width as compared to its side, and the windings are placed in a specific manner as shown here, both in case of core type transformer as well as shell type transformer. This manner of winding reduces the insulation requirement as well as reduces the current. Actually, it also reduces, uh, it actually also aids in reduced temperature of the core. Not actually reduced temperature of the core, you can actually say it provides better regulation of temperature in the core. Because the HV windings, you can see HV windings are exposed to air, while as LV windings are not. But since HV windings will be carrying are having more stress as compared to LV windings, so they will heat up more. So better cooling of the transformer using this mechanism, transformer windings rather. So, and also this core is not made up of a one solid block, it's made up of laminations, and these laminations are actually tapered at the center. The width of the limbs will be more as compared towards the peripheries, towards the edges. This actually makes room for uniform flux distribution, and laminations are used to reduce the eddy current losses in the system. So this is about the construction of the transformer. Now let's take up the principle of operation of transformer. Now talking about the principle of operation of a transformer, we'll be actually studying the ideal transformer today. So the basic principle of operation of a transformer is derived from Faraday's law, which actually states that when a coil comes in contact with a time varying flux, voltage is induced in that coil. So if we have any coil through which we can have a coil and it comes in contact with time varying flux, so voltage is induced in this coil. Right? The polarity of induced voltage can be basically determined using the dot convention, whether this time varying flux is passing through uh, clockwise winding or an anti-clockwise winding. So E induced is equal to the time rate of change of this flux minus d phi by dt, and if the number of coils is equal to n, then E induced is equal to minus n d phi by dt. And this minus here basically as given by Lenz's law actually suggests that the voltage, the actual cause of production, the flux will be produced because of some cause, and that cause will be a AC voltage here. The primary voltage will produce uh, the flux, and the polarity that will be induced in the secondary coil will actually, if connected in series with the primary winding, will oppose the original cause of this original cause that actually produced this voltage or induced this voltage in the secondary coil. So that is what minus suggests here. So E induced is equal to minus n d phi by dt. So the greater the rate of change of flux, greater will be the voltage induced in the coil. Fine. So you have, in case of a transformer, what you actually have is you have a winding, a primary winding, and you have a secondary winding. So the primary winding is actually excited using a voltage source VAC, or we write this VAC, we write this as VP, fine. And for the ideal transformer, this VP will be available at this point as well. This VP will produce a flux that will actually be associated. This flux will actually cut through the secondary coils and induce a voltage in the secondary coil that will be equal to Vs. And we'll assume that the polarity of this transformer given by the dot convention suggests here that Vs will be induced in this manner. Fine. That means actually the current will be flowing in this manner. And if the number of coils of the primary side is equal to Np, the number of coils of the secondary side is equal to Ns, the ideal transformer suggests that Vp will be available at the ends of the primary winding that will produce a flux phi that will cut through the secondary coils to a time varying flux produced because of the time varying voltage. This is a time varying voltage because it's AC in nature, so your flux that will be produced will also be AC in nature. If Vp is equal to Vm sin omega t, phi will also be equal to phi m sin omega t, ideally speaking, and that will cut the secondary coil segment, secondary windings, which will induce a voltage Vs in the secondary coil side. And the convention states that Vs will be equal to, as suggested from the Lenz's law, will be equal to minus n d phi by dt. Therefore, if we equate those equations, we'll be getting Vp by Vs equal to Np divided by Ns, right? Where Vp is the primary voltage, Vs is the secondary voltage, Np is the number of turns of the primary winding, and Ns is the number of turns of the secondary winding. Or you can also write this as Vp divided by Np is equal to Vs divided by Ns. This will be the voltage equation. The current equation will be contrary, opposed to this. Ip by Is will be equal to Ns divided by Np. Fine. So this equation suggests us that if Np divided by Ns is equal to, say for example, 10, that's this Np divided by Ns is equal to 10, Vp, uh, and Vp is equal to 230 volts, then Vs, the secondary side voltage that will be induced in this coil, will be 230 divided by 10, that will be equal to 23 volts. Fine. So if Np divided by Ns is equal to 10, that means number of turns of Np is greater than the number of turns of Ns. That means Vs will be less than Vp. So if Np is greater than Ns, Vp will be greater than Vs. And if Np will be less than Ns, Vp will be less than Vs. And also, if Np is greater than Ns, Is will be greater than Ip. So this is the operation of the transformer. It's given simply using the Faraday's law. Faraday's law states that time varying flux, when a time varying flux cuts a coil, it induces EMF in that coil. Now, this coil is not rotating. It not rotate. The flux itself is time varying and cutting through the windings. So this voltage induced in the windings will be equal to the time rate of change of this flux, that's minus n d phi by dt, where n being the number of turns of this coil. And the ideal transformer equation simply states that Vp divided by Vs is equal to Np divided by Ns. That's actually the turns ratio of this transformer. Fine. So, and Ip divided by Is will be equal to Ns divided by Np divided by Ns can be written as A, where A is known as the turns ratio. Uh, so this is your principle of operation of an ideal transformer, and we already discussed this, that the input power P in will be equal to the output power of this transformer. So if input power is equal to VPIP, the output power is equal to Vs into Is. So there will be no change in case of the input and the output power. The power levels of the transformer on either sides remains the same. Now, so this is all about the ideal transformer. If we'll actually do the practical transformer in the next session, also we'll look at, from there on we'll derive the equivalent circuit of the transformer and then the phasor diagram of this transformer. Right. Uh, so this is about the ideal transformer, where in case of ideal transformer we are simply assuming that there are no losses in the system. There is no loss means there is no core loss, there is no copper loss, there is no flux being lost in this system, and whatever amount of power is being fed to the primary windings, same amount of power is being received through the secondary windings outputs. So this is all about the ideal transformer operation. We'll be doing the practical transformer in the next session, the real time transformer.